First of all, what is nuclear fusion? Nuclear fusion is a process where two light atomic nuclei combine to form a heavier nucleus. It releases a large amount of energy. It is the same process that powers the sun and other stars. Fusion uses hydrogen isotopes like deuterium and tritium as fuel. The energy released is clean and has no greenhouse gas emission. This makes fusion a strong candidate for a sustainable and environmentally friendly energy. The image shows a nuclear fusion reaction where deuterium and tritium is isotope of hydrogen combine to form helium and neutron. This reaction releases a large amount of energy. It is the same process that powers the sun and has potential for clean energy production on Earth.
Why we choose this topic and its relevance to modern physics. First point, fusion offers long-term clean energy. Fusion produces no greenhouse gases during operation, unlike fossil fuels. Next, it uses abundant fuel sources like hydrogen from water and lithium. Last, no long-life radioactive waste, unlike nuclear fission. Second point is, it solves major global challenge, addresses climate change by reducing carbon emissions. Next, helps meet growing energy demands without harming the environment. Last, offers energy security for countries lacking fossil fuel resources. Last point is, fusion is at the frontiers of science and innovation. Combines advanced physics, engineering, material science, and AI. Next, involve cutting-edge projects like ITER, SPARC, and NIF. Lastly, encourages interdisciplinary research and global collaboration. In summary, nuclear fusion is a crucial research topic because it addresses energy, environment, science, and future global development all at once. It's a perfect choice for students interested in making a real-world impact. Methodology of gathering information. First, access academic journals and scientific publications through Google Scholar and Science Direct. Next, watch lectures and documentaries platforms like YouTube. Lastly, use official AI sites to get more information we needed.
Among the challenges are dealing with neutron radiation. Neutron radiation is a form of ionizing radiation that presents as three neutrons from nuclear fusion. When produced during fusion, it could travel and project damage to constituent material used on reactor. And other than that, we have fusion field. Massive gravitational forces in sun provide the idea for nuclear fusion. It's difficult to accomplish nuclear fusion on Earth as the Earth gravitational force is not an ideal condition for it to occur. So we move to the next, which is proposed solution. First, research with an intense research by experts through advance in plasma physics. Next, innovation, reducing neutron radiation by making insulator into a fusion reactor with a fusion relevant electronic field measurement. And lastly, materials, fast-flowing liquid coolant on first layer of a nuclear system.
Other than that, what the concept of nuclear fusion? Nuclear fusion is a process where two light atomic nucleus such as hydrogen isotopes like deuterium and tritium combine to form a heavier nucleus like helium, releasing a large amount of energy. This process occurs naturally in the sun and stars, where gravity creates extreme conditions. For fusion to happen on Earth, we need first, very high temperature around 100 million degrees Celsius to make the atoms move fast enough. 2. Extremely high pressure to force the positively charged nucleus close enough to fuse despite their naturally repulsion. 3. The released energy comes from conversion of a small amount of mass into energy according to Einstein equation E equal to mc squared. 4. Fusion is different from fission. Fission is used in current nuclear power. It's cleaner, safer, and produce less radioactive waste.
For the next part is law and theories, which is E equal to mc the power of 2. Theory introduced by Albert Einstein in his theory of special relativity in 1905. For the formula is E equal to mc the power of 2, where E for energy, m for mass, c for speed of light, which is constant 3 times 10 the power of 8. Application in fusion, when two light nuclei such as deuterium and tritium fuse, the mass of the resulting nucleus, helium, is less than the total mass of original nuclei. The missing mass is not lost but converted into energy as predicted by this equation. This is the source of energy in stars like our sun and the goal of man-made fusion reactor. After that, plasma physics. Definition: plasma is high-temperature ionized gas composed of ions and free electrons. It behaves very differently from solids, liquid, or gases. Relevance to fusion. Fusion occurs only in plasma conditions where temperature exceeds 100 million darjah 100 million Celsius. At this temperature, electrons are stripped from atoms, forming plasma.
Application in daily life. Imagine a future where our homes, office, and even our vehicles are powered by clean and safe energy. That's the promise of nuclear fusion. It has the potential to become a major source of electricity in our everyday life, offering virtually unlimited energy without the harmful emission of fossil fuels. From lighting up our cities to fueling electric transport, fusion could completely transform how we live.
How this concept is applicable in daily life. First, clean electricity for homes and business. It can provide massive amounts of electricity with zero carbon emissions. Reliable powering for lighting, heating appliances, and electronics. Next, lower energy bills in the long term due to abundant fuel. Second point is electric transportation. Electric cars, buses, and trains more sustainably. Next, potentially even supply hydrogen fuel for hydrogen-powered vehicles. Third point is powering industry. Cut emissions and reduce dependency on coal and natural gas. Last point is improve quality of life. Less dependence on imported energy. Next, fewer blackouts and energy disruptions. Last, healthier environments due to lower pollution.
So the career. Nuclear fusion also opens doors to many exciting career opportunities. You could become a nuclear physicist, working to understand the science behind fusion, or maybe a fusion reactor engineer, designing and building the technology that makes it work. There are also plasma researchers who study the behavior of the superheat gas inside fusion reactors. These professionals are at the forefront of a scientific revolution, turning fusion from theory into reality.
The ITER controversy. Firstly, project delays have been a major issue. The original completion date was set for 2016, but now it's been pushed beyond 2025. Secondly, we have cost overrun. The budget for ITER has tripled over time, which has raised serious economic concern among member nations. Finally, there is ongoing criticism regarding its feasibility. Many experts question whether the project will deliver a worthwhile return on investment, given the scale of resources being used. These challenges highlight the difficulty in bringing fusion energy from theory to reality. Achieving net position energy, the ongoing challenge. First, extreme conditions are needed. The fusion process requires temperatures about 150 million degrees Celsius to ignite the plasma. Second, the energy input is a big hurdle. We need to put in a lot of energy just to initiate and maintain the reaction. Lastly, we have to focus on efficiency. Right now, the amount of energy we get out is still less than what we put in, and that's a key obstacle scientists are working to overcome.
Besides its essential skills required in fusion energy and lifelong learning. First is physics. Understand fundamental principles that govern system behavior and interaction. Explanation for physics. Physics is the backbone of fusion energy. Understanding atomic structure, nuclear forces, electromagnetism, and plasma behavior is crucial. Fusion involves complex reaction between atomic nuclei, so a solid foundation in physics allows you to grasp how fusion reaction work, like the deuterium and tritium fusion. Understand magnetism confinement. Other than that, you can analyze the behavior of high temperatures plasma. In lifelong learning, physics enhances problem solving and critical skill thinking, which are essential across scientific and technological careers. 2 is thermodynamics. Gain expertise in energy transfer, system efficiency, and heat dynamics. Explanation for thermodynamics. Thermodynamics focus on heat, energy flow, and system efficiency in fusion energy. It helps optimize how energy is transferred from the plasma to usable electricity. It aids in designing cooling system to handle extreme temperature. Engineers use it to access system efficiency and minimize energy loss. In lifelong learning, mastery of thermodynamics supports your ability to design sustainable and efficient system, applicable in many energy-related fields. 3 is computer programming, gains expertise in energy transfer, system efficiency, and heat dynamics. For computer programming is key in modeling fusion process, running simulations, and controlling complex fusion systems. It helps to stimulate plasma behavior and magnetic fields, analyze experimental data in real life, and can develop software to automate reactor systems and safety controls. In lifelong learning, programming skills are highly transferable, enabling innovation and automation in various fields beyond fusion. 4 is teamwork. Collaborate effectively within diverse, multidisciplinary team for success. Other than that, for teamwork, fusion energy projects are massive and involve experts from physics, engineering, computer science, and more. Teamwork helps to communicate and collaborate across disciplines, solve complex problems together, foster creativity and innovation through diverse perspectives. In lifelong learning, teamwork builds emotional intelligence, leadership, and adaptability skills valuable in any career path.
That self-development. First thing first, stay up to date. How can it achieve? Try to secure an internship during your academic training at research institution, national laboratories. For goal setting, allow to secure a full-time position of those company to ensure future development in the next innovation. Besides, technical and research skill, how can it achieve? Which is obtaining a strong educational foundation in physics, engineering, or anything related. For goal setting, establish yourself as an expert in niche area of fusion research such as plasma confinement or reactor design. Moreover, innovation. How can it achieve? Undertake projects or contribute to innovation R&D initiative within the company you join. For goal setting, contribute to at least 2 significant research projects or publication in the field of nuclear fusion. And lastly, personal growth. How can it achieve? By seek mentorship from experienced professionals in the field, discuss your career goals and development. For goal setting, allows you to also mentor early career researcher and student which contribute to the next generation of fusion scientists.
Career challenges and solutions. Fusion is a niche and highly competitive field, so there are limited opportunities. A long educational journey is usually required, often a PhD, especially for advanced research position. But there are ways to succeed. Building strong network, gaining internship, and developing skills across multiple disciplines are key strategy to stand out and grow in this field. The long-term vision for fusion, in terms of commercial viability, fusion power is still decades away from being market ready. However, the environmental impact is promising. Fusion has the potential to be a clean and sustainable energy sources, helping combat climate change. Moving forward, continuous research, innovation, and global collaboration will be essential to turn fusion energy into a reality.
So the conclusion, nuclear fusion is not just a scientific dream, but it is a promising and sustainable energy solution for our future. While there are still challenges to overcome, the progress being made today brings us closer to a cleaner world. Investing in fusion research today means a brighter and more energy secure future for generations to come.